Strabala, Marshall. I think Marshall is from Chicago and everywhere, Shanghai and. Yeah.
Okay, thank you very much. My name is Marshall Strabala, and I'm the design partner of To Define Architecture. We started about a year and a half ago. And what I'm going to talk today is about the same building you just saw. I think Donald will love it because we use 4 pieces of glass on the facade, and Dow Corning will love it because we use 4 pieces of glass siliconed around it, and Uwanda loves it because they won the contract. M. Arthur Genser Jr. was the design architect. I was the director of design there from 2006 to 2010, and we've been hired by the client to carry through the completion of the building to 2014. Now, these projects are done by a huge amount of people, and I'm going to talk about something very specific very quickly. I'm going to talk about the movement of the A-wall, the outside skin of this tower, and it required the efforts of Tongji University, who's the architect of record. RWDI did the wind engineering, which was the pressures, the movements. Thornton Tomasetti did the structural engineering of the primary structure of the building and the primary structure of the curtain wall supporting structure. Cosentini did the MEP work, which we probably won't talk about too much, but there is an anti-condensation system on the facade. Ari Khan did the facade engineering. John Perry did a great job, and Jim Intel and Lee Fang of RJA played a bigger part than I thought they would in a curtain wall. Since this building is right now the 2nd tallest building in the world, it's the tallest building I know of that is a double skin building. The entire facade has 2 skins over it. Uwanda is the contractor for the outer skin. Jiang Ho is the contractor that's been appointed for the inner B-wall skin. And the client, I must thank them because I think they had the toughest job in the world. They had so many experts telling them things that just sifting through everything was a huge task. Movement. In a tall building, you have vertical movement up and down that affects the curtain wall. You have horizontal movement of rotation. You have deflection of beams and pipes. You have drift of the building. You have thermal expansion. You have creep of the concrete, settlement in the foundations, and then last but not least, our friend fire. And when we started the project, to go from a concept sketch to a final building are so many steps that I could talk about this for probably 2 days and bore everybody to tears. But the conference is about why tall. And when I thought about what we could talk about, I wanted to tie it into reinforcing what Uwanda's doing and go back a little bit to a report that TT developed. And the images of 311 in Tokyo scared me that there was so much movement caused by Mother Nature, that to reinforce what we studied and what we did on the building to make sure it's right when we do the curtain wall and develop it as we're doing right now, how safe, how green, and how humane are really the topic of the conference and the topic of how this curtain wall supporting structure works. So I always start with a plan. This is really the building the client sells. It's a tall set of cylinders that form the inside that we call the B wall, and then the outer skin is the A wall. Now, first of all, we have these zones, and we try to keep them consistent in the zone so the floor plates are the same. Where the outer skin actually tapers and twists, that's the force the wind sees. But the developer can sell very consistent floor plates. Then it became a question of, why would anyone want to do the world's tallest double skin building? And what are the metrics of that? If you take a square building of the same area as a round building, you have 14% less perimeter. So what we try to do is be sustainable by not building things. The round is the most efficient shape you can have for the least amount of curtain wall. And since we're building 120 stories of curtain wall, that's a good place to start. Then we add the outer skin. and try to minimize that too by making it as close to round as possible. We actually make it a Y shape or a triangle shape that's very soft, and we bring it as close as we can to the inner skin and try to keep this distance within 12 meters. So the atriums are usable, but not overly large. The volume of the atrium is about 1/6 of the volume of the inside space. So the Y-shape building, as we saw the first day, is very efficient from a structural standpoint. The round shape is very efficient from a curtain wall shape, and the square shape is very efficient from a core shape. The floors are increasing in movement as you go up. We start with 12 floors of occupied, 13, 13, 14, 14, 15, and 15. So the building gets taller to match the area so our lifts in each zone are consistent. And then we have 2 floors of mechanical where we put all the structural outriggers that Dennis talked about before. We put the areas of refuge in there and the mechanical. The B wall, the center one, I'll go through very quickly. We originally thought that would be a unitized system, and the outer wall A could be a unitized system or it could be a stick system. But the B wall actually became a hybrid of a partial stick system and a partial unitized system because of the fire requirements. A very simple wall. You've seen it on just about every high-rise you can come up with. Some design drawings showing the frit, the mullion shape from the outside and the inside. We tried to keep a consistency of detail. The building is shaped as a soft rounded triangle. The mullions are soft rounded triangles. But then with tall buildings, you get this big deformation, this movement, where one side of the building actually opens up and the other side closes down. We have opening deformation, closing deformation. And these are all the reports that TT put together. It's different for each level. If you look at level 3 down here, we have a closing deformation per floor of 33 millimeters. So we look for the peaks in order to solve our movement problem. At the top, there's a different dimension that we have to accommodate. So it's all these little points where the system changes that give us the biggest headache. The horizontal movement, the vertical movement, and we have one other movement. Since the A wall on the outside is separated by 12 meters and it actually moves independent from the inner wall, we have a movement joint in here. And then the fire response was a 1-hour fire zone here. So there had to be a detail that connected the struts that support the curtain wall to go through someone else's work that actually moves up and down. So we have very special movement in this building that doesn't exist in other buildings. And we have a fire issue. The Chinese fire code required us to develop an 8 megawatt fire response to get temperature gradients that RJA did that TT took to develop the quantity of intumescent paint on the structure, and then that also gave us extra movement. If you have an 8 megawatt fire next to a bunch of steel, it will expand. In fact, half of the movement that we have to accommodate in this point down here, which you saw in Tony's presentation, a slip joint that moves up and down, comes from a fire. And the principle of our design was to create a curtain wall supporting structure that would not collapse under fire. And it would not expand over the heat of the fire and have panels fall off after the fire was put out. The fire will break the panels here, that glass will fall, but then we had the onus of keeping other panels down the road from falling off. So the B wall, which we thought would be the easiest wall, actually became one of the hardest walls. The A wall, the outside, is more about geometry. So at the bottom, we have very big panels. They're about 2.2 meters wide by about 4.5 meters high. At the top, each level gets a little smaller by a couple millimeters. The top, it's 4.3. The 2 hotel zones have a 4.3 floor to floor. The office has a 4.5 floor to floor. But the tapering and twisting of the tower actually reduces as you go up. In the competition, we thought we could take struts at every other floor to make it more transparent. We cheated. The structural engineer said do it at every floor. We drew some images to make it more transparent, more lighter. Coming back, the pieces got so big we had to shift to a single strut system to support it. And we actually looked at cutting that down again with brackets that lasted for about, half a month or so. It was a very interesting system. We'll use it somewhere else. So we looked at the type of wall. If we just take a sloped mullion and put it over the skin, there are no right angles in this piece of glass. And on each floor, there's about 140 pieces of curtain wall. Only 3 of them on each floor were the same. So it became a disaster to even look at this. If we shingle it, and we have panels that overlap each other, it has 2 right angles, but then we have an irregular line here. I think we had about 8 or 9 panels, and maybe we could do that to 20 panels given a 10 millimeter difference. And we looked at these for a long time, and we finally settled on a very simple idea that was exactly how we designed the building. We took a shape, the shape of the outside skin, and we scaled it in 99.58 degrees. And we rotated it 0.81 degrees. And that became the next floor. So that was the methodology of creating the geometry, and it finally became clear that we would want to do that for the curtain wall. So every piece of glass is vertical. You could put a level on it, a plumb bob, know it's in place. We know what it is from the girt, and we take it out, and every piece of panel glass from this point all the way around, 130, 132 panels, are the same width. God, that was genius. We thought we were doing great. Lo and behold, not so good. Because what we had is now we had a shelf system that came around here that caused another geometric problem. But let me go through how the building is constructed to help you understand how the curtain wall then has to go on. So basically you build up to one of these amenity floors, and your core goes up faster than your floors. You throw in a couple sticks for the steel flooring, and then you keep building this up, and it goes up. There's nothing strange about it. And then you get to these amenity floors with the redundant belt trusses, and then the next floor, we have the radial trusses that are actually hanging the curtain wall and using this space that's not very good for mechanical for the area of refuge. The floor below it is a little bit cleaner for the mechanical and a little bit taller. And then we start again. It's like 8 typical buildings stacked on top of each other, but the center is consistent, the outside changes. So then you start hanging the curtain wall structure down. So you go up, then you go down. The rest of the building can go up, so you could have 2 crews working on this. Okay, so the shape of the structure that supports the A wall is basically a pipe. It's 350 millimeters in diameter, 25 millimeters thick, and it roughly has this shape, and there's 14 of them on a 14 floor, 13 on a 13 floor. We looked at supporting it as columns, where the weight is coming down. The columns got so big that you had a redundant set of columns on the outside of the building just to hold the glass. Didn't seem to make much sense, which is why we went to the hanging solution, because if you hang a system, you use less material, it's more green. The hangers are redundant. We have 2 hangers in case one comes down. The other one will support the system. If 2 hangers come down, the deflection increases, but the system will not fall down. The struts going back are about 250 millimeters thick. And you could see in the visual mock-up, the struts come in at a point, and we can actually create 3 points of X bracing to give rigidity in a horizontal, because this system transfers the wind loads to the superstructure loads. And then it's tied back at the 3rd point. So again, we have this Y structure, where there's a big block of structure in here that stops movement here, and the X bracing at this point stops movement in the other direction. We only had 1 bracing in the V strike, and then through an expert panel review, they said, well, we would like to see X bracing in the other wings, especially at the top, and then we took that theme through the building, and it seemed to make sense. We're making it strong, we're making it stronger. Oh, we made it too stiff. Now we have to put in expansion joints. because of our friend fire. But this is how the skin looks once you put the mullions on it and the glass. And this is the detail that you want to develop to try to get a little bit of vertical movement between each floor. The vertical movement is very, very small, maybe 2 to 4 millimeters at the most due to the elongation of the sag rods. The elongation from temperature will only interact that because this is one big hoop skirt that hangs down. We've ganged up all the movement at the bottom. So it's a simple, we try to put stainless steel up here to keep it to be cleaned easily, aluminum sections where it makes sense. But then geometry plays a trick on you. We have places where there's a big step and we have places where there's a small step. So we have just about every panel has something different on it. This is where Yuanda has the task of creating, the glass system is very uniform, but the attachment system back changes pretty regularly. So what you have is you have a deep panel at the bottom of 600, and then it actually goes under by about 50 millimeters. So there's a slight undercut, and then that reduces by 1/2 as we go up the building. This is just a slide showing the underside is very important because when you look up from the atrium, that's what you see. And we've worked with Yuanda adjusting the panels to make sure it fits and it's clean and it's tidy. The frit that someone spoke about is put on the number 2 surface of a laminated low iron glass for the outside. It's 10 millimeters thick, 2 layers of it for safety. In case one layer breaks, you see it broken, it doesn't fall out of place. But the frit from the inside, you see this high contrast photo, actually reduces the total energy consumption of the building by about 3%, 2.5 to 3%. So it's a shading device, it's an anti-glare device, and it actually gradates down to 0. The deflection of the girts between the sag rods has a maximum of about 27 millimeters at the bottom and 5 millimeters at the top. The movement is all condensed around this point. So this whole wall moves up and down about 250 millimeters in its worst case. Could go up about 200 and down 250. About 60% is non-reversible due to creep of column shortening and stretch of the steel. And it depends on how you actually put the steel in. If you camber the steel or if you shorten the sag rods as you put it in, it makes a difference. This is one of the last slides. It's Jan Ho's visual mock-up of the A and the B wall, sort of standing up here looking down on it. So this is probably one of the first images you see looking down into the atrium that's pretty close to reality. You could see the sag rods here and the mullions going up. So we have a system we think is very good, very, very thoughtful, simple, it follows the geometry, it accepts the restrictions that the structural engineer put on us, it accepts and integrates the restriction the fire department put on us, and it really tries to make a safe, tall building with redundancy, with simplicity, with constructability. And it's probably one of the most complicated things I ever had to do in my life. I feel honored to have worked on the project. We won the competition in 2006, and now we're going to carry it through with a client till 2014. So go back to this idea about why tall. Why do we build tall buildings? I agree with Jan Clerks. I love tall buildings. I think they're great. I didn't start out as an architect wanting to do tall buildings. I just happened to end up doing them a lot. But really, it's a why tall, and I think Adrian had a great joke and he never took advantage of it. So why tall is very good, but I like to say, why not tall? So thank you very much. I think everybody will have a nice lunch.
Thank you, Marshall. Marshall's presentation is more like the strength of materials. He talked about the movements, deformation, deflections, and it's very interesting.
Yeah, we did this about 1.5 years ago, and so it was good to come back to it because now we're working with Yuanda on this. So it was a refresher course for me.
Any question for Marshall?
Marshall. My question is not about the building skin. It's more about the building itself.
Okay.
You emphasize that the core is efficient when it's rectangular, and then floor
Yep.
plate, circular, and then triangular structurally. But when you put this all together, how efficient is your building in general and money-wise and for interior, the uses of the interior space?
Okay, that's a very good question. The efficiency of the core to the gross area is about 62% because you're stacking so many different elements on top of each other. The core corners step back as the cylinders get smaller. So the four corners of the core sort of disappear to increase the usability. And the two top ones are hotel, so the lease span there is 8 to 9.5. The lease spans at the top office are roughly about 10.5. The lease spans at the bottom go up in excess of about 15 to 18 meters. The bottom floors are very good for insurance companies, large call center types. The top office zone is very good for attorneys. Since you don't have one user, the different types of floor plates will be enhanced by the different users. The big question, and I think you were alluding to, is the cost of the double skin, which is why we went to the circular forms to use less material to create a double skin. And in reality, the premium is not 100%, it's only 30%. If you go back to that slide where I showed the square building next to our building, if you take a tapered building like the John Hancock, you know, in Chicago, and you take the Shanghai Tower of the same area, there's only 30% more glass in the Shanghai Tower. I've done this about 9 times and I keep coming up with the same number, and it scares me it's so low. But the mechanical floors are what do it for you.
Hello. Actually, 2 questions. First, could you mathematically answer the question yesterday to the Gangster speaker? What's the payback period of the double skin system? And second, what's the design, where the design goes after RWDI provided the very convincing wind tunnel test? Thank you.
Could you repeat the second question? And by the way, you're not allowed to ask questions.
How the design evolved significantly after RWDI provided the wind tunnel test, the 6 kPa issue?
The first question was about the payback. The payback is about 9 to 10 years, depending on the cost of energy. And that includes the cost of the steel and the cost of the extra glass, 30%. The second question is, how did the design develop after RWDI did the original wind tunnel? The design in competition, we just guessed at 120, 3 buildings, 3 brothers. This building would rotate 120 degrees. It looked about right. And I sent the design to Peter Irwin of RWDI, and we talked about it, and we introduced the strike as a spoiler, and we kind of had the building sited about 90 degrees off of where it ended up, but that didn't make a difference. RWDI did the first wind tunnel test, and it was an experiment in what the twist should be. The client said, Marshall, don't make the building bent. We tested a 180-degree twist, and we tested a 90-degree twist. And we found the more twist reduced the loads on the building, but the more twist made the building look bent. You have to go to almost 360, 420-degree twists to get it to not look bent. So working with RWDI, the client, the structural engineer, we kind of came to a conclusion that the 130, 134-degree twist visually looked right, reduced the loads of the structure by about 24%. And when I say reduce the loads, it's reducing the loads from a theoretical model of a tapered rectangular building. We as humans can't see things. We can only see the difference between things. So we tested a John Hancock building of the same area, the same height, against the Shanghai Tower, and we found that the twist reduced the loads by 24%. So it was an investigation of performance-based design, not a foregone conclusion. And we ended up about 14 degrees off of what the competition was. Any other questions? Dave McLean? Well, thank you very much.
Thank you, Marshall. I don't have a question. It's just my time or my duty to go over the summarization of each and every speakers. They were all excellent. They're from different countries, but we're talking about the same subject. It was great, and it is very important. I would say more than 1/4 of our efforts for high-rise buildings should be spent on this subject. Anyway, the first speaker was Mr. Krautzmeier from Germany, and he talked about the pressurized fire extinguisher and the water mist. It's new. It is very important. Before and after 9/11 in New York, the fire is very important subject for the building. Next speaker was Don McCann. Well, he's great. And unfortunately, we cannot spend a whole lot of time for questions. And I think people like to get hold of you to ask questions. Please spend your time for the questions. Sorry, I cannot spend more time. Another subject was Jin Young Jung from Dow Corning. That was also very impressive, especially wavelength versus energy graph was very valuable technical data. I like to, this is my personal opinion, I like to go into more technical subjects such as Young's modulus and allowable stresses and multi-layer. In case of multi-layer, what would be the stress and shear stress for each and every layer and so forth. It's my personal opinion. Another one was Tony Wang from Shenyang, China, and he is, like anyone else, was excellent. Also, his air pressure balancing device was very a good idea, and he really should not show the details at this conference. He should get a patent first before he show. But anyway, we are so grateful for his presentation. The last one was Marshall, and Marshall just finished it. And it was like he treated, unlike other presentation, he mentioned, not through the equations, but he mentioned about deformations and deflections, which is also a very important subject for structural engineering, structural design, as well as curtain wall design. So thank you very much for your patience, and let's keep in touch. Thank you.